This is applications of Extrema of functions of two variables. So it combines what we've seen already with Extrema with word problems. Let's take a look at our first problem here. Find the minimum distance from the point to the plane x plus y minus z is equal to 5. And it gives us a hint. To simplify the computations, minimize the square of the distance. Well, if we look at this x plus y minus z is equal to 5, we can solve this for z. So I'll take the 5 over to the left side. So we've got x plus y minus 5, and I'll take the negative z to the right and it becomes a positive z. Which means, taking that into account, we're going to have the point 2, 3, negative 5. And we'll also have another point, x, y, and then z, which we said z was x plus y minus 5. Now this is a very specific point here, and this is just a generic point that's on that plane. And again, what we're trying to do is we're trying to find the minimum distance from the point to the plane. So you got a plane out there in space, 3D space. And of course it goes forever in all directions, and you got a point up here. And if you look at the distance from that point to any point on a plane, there's going to be one particular place where it's a minimum distance, and that's what we're taking a look at here. Well, normally our formula for the distance is equal to distance is equal to subtracting your x values. I got x minus 2 squared. Subtract your y values, so I got y minus 3 squared, and then subtract your z values. So we got x plus y minus 5 minus a negative 5 squared. Which gives us x minus 2 squared plus y minus 3 squared plus negative 5, and negative negative becomes a positive 5, so those cancel, and we got x plus y squared. So that's our distance working with. Now our goal on these is we don't want z on this right side. We want everything in terms of x's and y's. Now it gives you a hint here. To simplify the computations, minimize the square of the distance. So we're going to minimize just what's inside of the square root. So, and I'll make it a uppercase D just so it's a little bit different. Got x minus 2 squared plus y minus 3 squared plus x plus y squared. So this is what we're working with. You would get the same results if you had left the square root there, but if you're minimizing this, that's the same as minimizing the square root over it. Well, we need to find the partial with respect to x. Well, this here we have parentheses to a power. Take a power, put it out in front. What's inside the parentheses remains as is. Lower your power by 1. And we multiply it times the derivative of what's inside the parentheses with respect to x, but derivative of x minus 2 is 1. Now this y minus 3 to the second power, that's just a constant, so that drops away. Plus 2 times x plus y to the first, times the derivative of what's inside with respect to x, which would again be 1, so that drops away. Now partial with respect to y. This has x's in it, so that drops away. The y minus 3 squared, take power, put it out in front. Lower your power by 1. Same thing here. And again, when multiply times the derivative of what's inside with respect to y, it's a 1 in both cases. So this gives us 2x minus 4 plus 2x plus 2y, which gives us 4x plus 2y minus 4. And this one, 2 times y is 2y, 2 times negative 3 is negative 6, plus 2x plus 2y, which gives us 2x plus 4y minus 6. Now we want to solve these two equations simultaneously, set them equal to 0. So we're going to have 4x plus 2y minus 4 equal to 0. And we'll have 2x plus 4y minus 6 equal to 0. Now I can take the negative 4 over to the right side. So we've got 4x plus 2y is equal to 4. Take negative 6 over here, and we've got 2x plus 4y is equal to 6. Now first off, I notice that they're both equations, everything's divisible by 2, so I'm going to do that. That gives me 2x plus y equals 2. And this one gives me x plus 2y is equal to 3. Probably substitution is the easiest way to do this particular one. I can solve this first equation for y. So I'll take the 2x over, so I got y is equal to 2 minus 2x. And we're going to substitute that into our other equation. So we got x plus 2 times 2 minus 2x equals 3. 2 times 2 is 4. 2 times negative 2x is negative 4x equals 3. X minus 4x is negative 3x plus 4 equals 3. Take the 4 over, and we get 3 minus 4, which gives us negative 3x is equal to negative 1, or x is equal to 1/3 when we divide both sides by the negative 3. Now we can easily find y, because remember y was 2 minus 2x, by plugging the 1/3 in here. So we've got y is equal to 2 minus 2 times 1/3. 2 I can rewrite as 6 over 3 minus 2/3. So we get y is equal to 4/3. Now we can find z from up above. We said z was equal to x plus y minus 5. So x plus y minus 5. X we said was 1/3, y is 4/3, minus, and I'm going to go ahead and rewrite the 5 as 15 over 3 to get a common denominator. These all have the same denominator, so I'll add / subtract top parts. 1 plus 4 is 5, minus 15 is negative 10/3. So, our minimum occurs at this point. So minimum occurs at the point x is 1/3, y is 4/3, and z is negative 10/3. So that's where my minimum occurs at. But let's actually find out what the minimum is. From up above, we said the distance is equal to x minus 2 squared plus y minus 3 squared plus, what was it, x plus y? X plus y squared. Okay, so x we said was 1/3, so we got 1/3 minus 2 squared plus y, which is 4/3 minus 3 squared, plus 1/3 plus 4/3 squared. This is a mixed number. We can take negative 3 times, or negative 2 times the 3, that gives us negative 6, and add to 1, and that gives us negative 5/3. Here we can take negative 3 times 3, it gives us negative 9 plus 4, that gives us negative 5/3 squared. And 1/3 plus 4/3 gives us 5/3 squared. Which gives us 25 over 9 plus 25 over 9 plus 25 over 9. Which gives us 75 over 9. split this up into square root around top, square root around the bottom. 75 is 25 times 3, so that gives me 5 square root of 3, and square root of 9 gives us 3. So that'd be our minimum distance right there. And this is the point where it occurs at. They're not asking for that, but if you're real curious, that's what that would be. What's this one called? Applications Extrema functions of two variables. So let me save that. Applications of Extrema of functions of something. Two variables. Page 01.pdf. There we go. Let's look at our second problem. We got find three positive integers x, y, and z satisfy the given conditions. Product is 8, and the sum is a minimum. Product is 8. Well, that means that x times y times z is equal to 8. And the sum is a minimum. So our sum, I'll say s, is equal to x plus y plus z. And we want to minimize this. Well, we want everything over on the right side to just be x's and y's. So over in this one, we're going to solve this for z. So I'll divide both sides by xy. And x is equal to 8 over xy. And now we can plug that in for the z. So we got x plus y plus 8 over xy, which I can rewrite as 8 x to the negative 1 power, y to the negative 1 power. These are both x to the first power, so I can take them up on top with the 8, and they become a negative 1. Well, now we want to take the partial with respect to x. Well, the x will become 1, the y drops away. Now here, the 8 and the y to the negative first is the constant part, so we'll work with x to negative 1. So take your power, put it out in front, lower your power by 1, like that. That gives us 1 minus 8 over x squared y. Take the x to negative 2 and y to the negative 1 back downstairs. Take partial with respect to y. The x drops away, the derivative of y is 1, minus 8, and then the x to negative 1 is constant, so that stays there. And we put that power out in front, so this is now y to the negative 2. Which gives us y minus 8 over x y squared. Now we want to set those equal to 0 and solve them simultaneously. So we've got 1 minus 8 over x squared y is equal to 0. And here we got 1 minus 8 over xy squared is equal to 0. Now I'm going to take the fraction over to the right side. So we got 1 is equal to 8 over x squared y. And 1 is equal to 8 over x y squared. Here I'm going to multiply both sides by x squared y. So that gives us x squared y is equal to 8. And on this one we'll do the same thing, except for multiply both sides by x y squared to get rid of the fraction. And that gives us x y squared is equal to 8. Now we want to solve one of these. I'll solve the one on the left for y. So y is equal to 8 over x squared. And we want to substitute that into the other one. But actually I'll solve this for x first. I'll divide both sides by y squared. And we get x is equal to 8 over y squared. And over here we said y is equal to 8 over x squared. So we'll replace the y here with 8 over x squared. Which gives us 8 over 64 over x to the fourth. Complex fraction. We'll multiply the reciprocal of the bottom part by the top, so that gives us 8 times x to the fourth over 64, which gives us x to the fourth over 8. The 8 and 64 reduce. Multiply both sides by 8, and you get 8x is equal to x to the fourth. Take the 8x over, and we got x to the fourth minus 8x. Factor out an x, and that gives us x to the third minus 8. And I guess I'll continue it right here. Now if we set, this is zero factor property, we set the x equal to 0, and we set the x to the third minus 8 equal to 0. They tell us that the product is 8, so there's no way x can be 0. So that answer goes away. It doesn't make any sense. Here I'll take the negative 8 over, becomes a positive 8. And I'll take the cube root of both sides, 1/3 power of both sides. You can always get rid of an exponent by raising both sides to the reciprocal of it. So 3 over 1, the reciprocal of it is 1/3. So those 3's would cancel, and I got x is equal to the cube root of 8. And with the cube root, we're looking for something times itself 3 times. 8 we can rewrite as 2 times 2 times 2, which means that x is equal to 2. Well, from up here, remember we said y is equal to 8 over x squared. So, and y is equal to 8 over x squared. So if I put 2 in for the x, I get y is equal to 8 over 2 squared. 8 over 4 gives us 2. And they tell us the product is 8. And from that we said that z is equal to 8 over xy. So z is equal to 8 over xy. And x was 2 and y was 2. So that would tell us that z is equal to 2. So we got x is equal to 2, y is equal to 2, and z is equal to 2. And those would be our answers. Let me save that. And tablet blew up, so let's bring another copy up. There we go. Where's my... there it is. Let's take a look at this problem. It says a rectangular room is having the walls and ceiling painted. Rectangular room. Okay, so I'll label this side as Z, this side is X, and this side going back as Y. And see what else they say. Okay, the volume of the room is 1,000 cubic feet. Well, volume of a rectangular solid is X times Y times Z, and they tell us that's equal to 1,000. Now our cost, which is what they're focusing on here, says the cost of the wall paint is 5 cents per square foot wall paint. So we got 5 cents per square foot. So we need to take this 5 cents times the area of the walls. Well, if I look at the side over here, this side here is Y, this side is Z. So that'd be YZ. And there's another one over on this other side that's the same size. So that'd be 2YZ plus, if I look at this wall right here, this distance is X and this height is Z, so that's BXZ. So this would be 2XZ. So those are our walls. Two of them, because again I got one back here at the same dimensions. Now our ceiling. Cost of ceiling paint is 10 cents per square foot. So that's going to be plus 10 cents times our ceiling. Our ceiling here, this distance is y, this distance is x, this would be xy. Well, I can take this 2 and factor it out and put it out in front. That gives us 0.1. We can take 0.05 times 2, and that leaves us yz plus xz plus 0.1 xy. Now, again, over on the right side, we want everything in terms of x's and y's. We don't want z's in there. So we're going to take the other equation and solve for z and simplify a little bit. So we'll divide both sides by xy. So we've got z is equal to 1,000 over xy. And now let's plug that in. So we've got 0.1 times y times z. So 1,000 over xy plus x times z, which is again 1,000 over xy plus 0.1 xy. And again, we want to simplify this a little bit now. If I take the 0.1 and multiply it times 1,000, that gives me 100. And these y's are going to cancel, so that's going to give us 100 over x plus 0.1 times 1,000 is again is 100, and these x's cancel, so that gives us 100 over y plus 0.1 xy. That's probably not the easiest form to take the derivative, so I'll take the x at first, move it up on top. So we got 100 x to the negative 1 power plus 100 y to the negative 1 power plus 0.1 xy. And now we're ready to take our derivative. So I'll take partial with respect to x. Here's 100 x to negative 1. Take your power, put it out in front. So we've got negative 100 x, lower it by 1, negative 2. This doesn't have any x's in it, so that's a constant, so that drops away. And then we'll take the partial with respect to x on the last part here. The 0.1 and the y are the constant, and derivative of x is 1. So that gives us plus 0.1 y. Now the partial with respect to y, this just has x's in it, so that drops away. That's a constant. And here 100 y to the negative 1. Take your power, put it out in front. Lower your power by 1. And then this last part, we'll take the partial with respect to y, and that gives us 0.1x. Now we want to set these equal to 0 and solve them simultaneously. So this is negative 100 over x squared plus 0.1y equal to 0. And this one is negative 100 over y squared plus 0.1x and set it equal to 0. Again, we'll do a little bit of simplifying. Take the negative 100x squared to the right side, so I got 0.1y equals 100 over x squared. And here I'll have 0.1x is equal to 100 over y squared. If I divide both sides by 0.1, we're going to get y is equal to 1,000 over x squared. And this one will get x, divide both sides by 0.1 again, we'll get x is equal to 1,000, over y squared. That seems weird. When you divide by 0.1 it becomes bigger, but if you actually plug it in your calculator, you'll see that's right. Now this one's already solved for y, so we're going to go ahead and plug that into the other equation. So I got x is equal to 1,000 over y squared, so we'll have 1,000 over x squared squared. That's x equals 1,000 over 1,000 times 1,000 over x to the fourth, which simplifies a little bit. This 1,000 here cancels with one of these 1,000s. So we've got 1 over 1,000 over x to the fourth. Take the reciprocal of that, multiply it times your top part, and we got x to the fourth over 1,000. Multiply both sides by 1,000, and we get 1,000x is equal to x to the fourth. Take that over to the right side, and we got 0 is equal to x to the fourth minus 1,000x. Factor out an x, GCF, and we get x to the third minus 1,000. Now, if we set x equal to 0, that means we have no dimensions in our room, because if x is 0, then our volume is 0, and the room doesn't exist. So when we set x equal to 0, we can just immediately cross that one out. And we got x to the third minus 1,000 equal to 0. I can take the 1,000 or the negative 1,000 to the right side, becomes a positive 1,000. We saw this in the last problem. I just take the cube root of both sides. And 10 times 10 times 10 gives you 1,000, so x would equal to 10. Now the question is, find the room dimensions. So we need to find x, y, and z first, and then we'll find the cost. Well, y is equal to 1,000 over x squared. I guess if I go over here, I'm running out of room. So y is equal to 1,000 over x squared. And x was 10, so we got 10 squared, which is 100, which tells us y is equal to 10. Now, also from above, we got z is equal to 1,000 over xy. So z is equal to 1,000 over xy. So we got z is equal to 1,000 over 10 times 10, which tells us z is equal to 10. So our dimensions are that x is equal to 10, y is equal to 10, and z is equal to 10. So perfect square room. Now our cost from up above. Let's see what c was. C was equal to 100 over x plus 100 over y. So 100 over x plus 100 over y plus 0.1 times xy, was it? Yeah, xy. So if we put that in there, we got 100 over 10 plus 100 over 10 plus 0.1 times 10 times 10. Just plugging in our x and y values. Which gives us 10 plus 10 plus 10, which gives us $30. And that would be everything they're asking for. So I'm going to go ahead and save this. Oops. And go ahead and stop the recorders.